Problem number 3 of the Proofs 2 set is certainly algebraically the hardest problem that's on this entire sheet of Proofs 2. It's issued there as kind of a challenge for you. But before you take it on, make sure you're comfortable with exponents. And you might want to look through this hint where we kind of explain what the different expressions mean. You really need to understand the problem before you try to start solving it by induction. So you may want to do several cases. What I'd like to do is show you what it's saying here on both the left-hand side and the right-hand side. First of all, let's start with the left-hand side. Now, what is the first term we're going to work with here? Well, it says it's for all integers greater than or equal to 0. All n greater than or equal to 0. So we're going to start when n is equal to 0. And when n is equal to 0, let me write my summation over here. We're going to have 0 plus 1 at the top, I equals 1 down here at the bottom of the summation, and it's I times 2I. So we're going to go from 1 to 0 plus 1. In other words, we're going from 1 to 1. There's going to be just one term. And the value of I in there is going to be 1. So it's 1 times 2 to the first, or 2. When n is equal to 1, let's do our summation now. The summation now starts at I is equal to 1 and goes to 1 plus 1, or 2, so there will be 2 terms. So it's 1 times 2 to the first, plus, now we're going to do 2 in the position of I, 2 times 2 squared, which is going to be 2 plus 8, or 10. Now this final answer over here really isn't as important as noticing the pattern that you have as we continue with this. When n is equal to 2, we're going to do the sum going from 1 to 2 plus 1, which means there's going to be 3 terms, I times 2 to the I, which is going to be 1 times 2 to the first, plus 2 times 2 squared, plus, we end at 3, 3 times 2 to the third. I'm not even going to do the sum at this stage. If you'd like to do that because it helps you see what's going on, then go right ahead. I'm more interested in the pattern. When n is equal to 3, what's this pattern going to look like? I'm going to not write the summation symbol again. Well, I might as well. Let's do it one more time. Let's write the summation symbol. I was a little concerned about space, but I'll just keep pushing the paper up. We're going to go from 1 to 3 plus 1. I times 2 to the I. So it's going to be 1 times 2 to the first, plus 2 times 2 squared, plus 3 times 2 to the third. And now we're ending at 4, so it's 4 times 2 to the fourth. So if we went on and say that n equals 4, that's going to be 1 times 2 to the first, plus 2 times 2 squared, plus 3 times 2 to the third, plus 4 times 2 to the fourth, plus 5 times 2 to the fifth. Notice the last term always has a coefficient or multiplier and an exponent that is 1 larger than our value for n. Well, let's see, before we leave this, if we can do this in general, because that'll be really helpful. Suppose n is equal to k, something we're going to have to deal with in our assumption. Then we're going to be doing a summation that starts at 1 and goes to k plus 1. You notice when this is k, the last term is going to end with a k plus 1. If we expand this, it's going to expand the same way we've been doing all along. 1 times 2 to the first, plus 2 times 2 squared, plus 3 times 2 to the third. But how does it end? What's going to be the last term? Well, you notice the last term here was 1 more than n, because it was 1 more than n. So our coefficient out here is going to be k plus 1, and our exponent matched that, so it's going to be 2 to the k plus 1. Now, just as an aside, you might want to think for a second about what the term before that would look like. The term before that is going to have the coefficient being 1 less and the exponent being 1 less. So being able to expand this for n is equal to k is really useful. When you do the proof, you're also going to have to examine when n is equal to k plus 1. Which means you're going to do the summation starting at 1, going up to k plus 1 plus 1. In other words, it's going to go up to k plus 2. That should give you a big hint on what the last term of this one should be. Now let's stop for a bit and we'll do a hint on the right-hand side. Now let's look at the right-hand side of this expression. Notice it says that it's n times 2 to the n plus 2 plus 2, and it says it's for every n that's an integer starting at 0. We saw how the starting at 0 was important before. So what's the first case? The first case here is when n is equal to 0. When n is equal to 0, what do you have? 0 times 2 to the 0 plus 2 for the exponent plus an additional 2. Well, 0 times anything is 0, so this thing simplifies to 2. Might be important for you to look at how this right-hand side matches up with the left-hand side for this same case. When n is equal to 1, we get what? 1 times 2 to the 1 plus 2 is the exponent, and then add another 2. So this is saying 1 times 2 to the third plus 2. 2 to the third is 8. 1 times 8 is going to be 8. Add 2. We get 10. Notice that matches what we got for n equals 1 on the left-hand side. When n equals 2, what is this going to be? It's going to be 2 times 2 to the 2 plus 2, and then down here, plus 2. Well, this is 2 times 2 to the fourth. In other words, it's 2 to the fifth plus 2. You may want to compare that to what you get as a numerical answer when n is equal to 2 on the left-hand side. Well, what is it going to be when n is equal to some variable k? We just stuff in k for this thing. When you stuff in k, you're going to have k times 2 to the k plus 2 plus 2 is the expression. And when you make this equal to k plus 1, what are you going to have? Well, you're going to take k plus 1 times 2 to the k plus 1 plus 2, and then add another 2. Or in simplified form, I know it doesn't look that simple, k plus 1 times 2 to the k plus 3 plus 2. Those hints should help you in being able to do number 3. It is a bit of a challenge problem. Doubt that many of you would be able to fit it into that little space there, so be prepared to use a whole piece of paper for this one. But try it. I think if you work through it and remember your rules for exponents and you follow the pattern we've been doing, you can be able to do this.